Hey folks, it's chemistry time. This is Miss Gray, and we're working on podcast 5.1 where we're going to determine whether our compound is ionic or is it covalent. You see, compounds are what happens when atoms join forces. So all of these are going to be made from two or more different kinds of atoms. Let's first talk about forming ionic compounds. Ionic bonds form when electrons are transferred from one atom to another. There's my pen. There we go. So we remove electrons from one atom and add them to another. So the bond represents the force of attraction of a positively charged particle and a negatively charged particle. Here's some examples. In these particular types of ionic compounds, you'll notice that the positive charges are completely surrounded by negative charges, then the negative charges on all sides are surrounded by positive charges. That way we don't have any more repulsion of like charges than would be necessary. So these orderly arrangements of atoms are called crystals, and that's why they make such neat and interesting shapes. Fluorite is the bond between calcium and fluoride. And then, what's that one in the middle? Cinnabar. Mercury and sulfur joined together to make cinnabar. And then hematite is iron and oxygen in a particular crystal structure. So all of these minerals can be used to form rocks or even to form gemstones. Ionic compounds have certain properties that we can predict because of their ionic nature. Then we know they're typically going to be solid at room temperature because they have very high melting points. Usually they melt at temperatures that are greater than 300 degrees Celsius. So it has to get really hot for them to melt. That's why they're solid at room temperature. Another property of ionic compounds is that they're good conductors of an electrical current when they are either melted or when they're dissolved in water. Another property for ionic compounds is that they are highly soluble in water. In other words, they dissolve easily in water. Ions then are typically arranged in a regular repeating pattern that minimizes repulsion and maximizes attraction. We call this the crystal structure of the ionic compound. Another feature of ionic compounds is that they're made of what's called a formula unit, where we could represent the ratio of one atom to another in its simplest form, and that's what's called a formula unit. So it's a ratio, in simplest terms, of one type of atom to the other. Let me show you why we do this. Let's go back and look at the crystal structure of these ionic compounds. If you'll notice in these crystal structures, there's not simply one calcium ion and one fluoride ion. There's many different ions in this arrangement. Oh, I don't even have calcium and fluorine. This one is cesium chloride. And so the ratio of cesiums to chlorines overall in the general structure is going to be 1 to 1. Whereas sodium chloride, we can count, and we'll see in this picture, this is also a 1 to 1 ratio. For every sodium we have another chlorine. But in rutile, which is the mineral from which we would obtain titanium, it's the ore for titanium. Rutile has a 2 to 1 ratio of oxygen to titanium. So the crystals are arranged so that we can have exactly the right ratio of atoms but minimize the repulsion of like charges. So now let's look at covalent compounds. Covalent bonds are formed by the sharing of electrons, not the transferring of electrons. So, because electrons are shared, atoms can form double, single, triple bonds even to satisfy the octet rule for each atom. Remember, 8 is our stable number right? Except for hydrogen, which only needs 2 because it's filling in that s, the 1s orbital. So however they arrange themselves in order to accomplish that, that's going to determine its molecular structure. So here's an example of water where we have a single bonded oxygen sharing electrons with hydrogen on either side. Ammonia is where nitrogen would share electrons with 3 hydrogens. And then methane is carbon with 4 hydrogens. Notice how hydrogen gets involved in lots of different things here. And then carbon dioxide, of course, is 1 carbon with double bonds to each oxygen in its molecular structure. Let's look at properties of covalent compounds. Unlike ionic compounds, which were solids at room temperature, covalent compounds can be solids, liquids, or gases. They tend to have lower melting points, which compared to ionic compounds means something less than 300 degrees Celsius, and they have lower boiling points as well. They're not always soluble in water. Think of things like oil and, paint thinner. They're not very soluble in water. They are poor conductors of electricity, generally speaking, although sometimes they can be good conductors, so we'll call this variable, whereas ionic compounds are always good conductors. Oh, that's it for covalent bond properties. All right then, we'll look at metallic bonding. Metals have closely packed cations with a sea of mobile electrons moving freely around them. So in other words, those valence electrons, they don't stick to just one nucleus. They get to freely move from one metal nucleus to the other. So metallic bonds form due to the attraction of those free-floating valence electrons for the positively charged metal ions that they've left behind. So that's metallic bonding. Here's a picture to show you some of the types of metallic bonds that could form. So chromium and gold, I've shown chromium has this sort of arrangement in its atoms where they closely pack all of the nuclei so that the electrons wouldn't have too far to move. Gold is the most dense of the metals, and so it's packed even more tightly together. And then zinc has this hexagonal type of structure. So it allows for tightly packed, positively charged cations. This gives metals their properties. Having the electrons free to move allows them to be excellent conductors of heat and electricity. They're also considered to be ductile, which means they can be drawn into wires. Another feature of metallic bonds is that metals are called malleable. They can be forced or hammered into different shapes without shattering. They crystallize in characteristic patterns, and they're often alloyed together to enhance the natural properties of individual metals to make their traits more desirable. For instance, if you've ever worn like gold jewelry, gold is too soft and it will bend and deform. So to make it stronger, they mix it together with zinc and with copper to make different values of gold, like 14 karat versus 24 karat. So how do we decide which one is which? If you're looking at a compound and you're not sure what it is, here's your clue. If you see a metal that's bonded to a nonmetal, then we know that is an ionic bond. So if it starts with a metal and then it has a nonmetal after it, it's ionic. If all you have is nonmetals, then of course that's covalent. And then this one's the most obvious, right? If you have metals bonded together, then those will certainly form metallic bonds. I know, Captain Obvious here, metallic bonds formed by metals. So now let's look at some of these examples. Here I have KNO3. This is called potassium nitrate, and I notice right away K, potassium, is an alkali metal, and N is a nonmetal, so that's got to be ionic. The next one, number 2, is iron oxide. Iron is certainly a metal and oxygen is not, so that one's ionic. Number 3 is carbon dioxide. Carbon is a nonmetal, and so is oxygen. So this one we would call covalent. All right, number 4, nitrogen, nonmetal, oxygen, nonmetal. So, whoops, we call this covalent because it's entirely made up of nonmetals. Number 5 is copper sulfide. We all know copper is a metal. Look on your periodic table if you're not sure about sulfur. You're looking for the staircase thing. Anything to the right is a nonmetal, and anything to the left is a metal. So, find sulfur. It's over on this side of the nonmetals, so that makes this ionic. All right, carbon is a nonmetal. Hydrogen is a nonmetal, and so number 6, CH4, must be covalent. Right, number 7 might look familiar. C6H12O6, this is glucose that's made in the process of photosynthesis. And of course, since that's entirely made of nonmetals, that is a covalent compound. And then the last one we've got is bronze. Bronze is an alloy of copper and tin. And since copper and tin are both metals and they are alloyed together, then they are held together by metallic bonds. And that's it. That's all you need to do to decide whether the compound you're looking at is ionic or covalent. The end. All right, I'm going to have a slide for you. I want you to send me a text message and respond to this question.